so identifying a chiral center. So here's the thing. Well, let me just define it and then I'll talk about it. If a single atom is bound to 4 unique groups, then it is a chiral carbon. Okay, that's actually what we just said up here. We just defined it up there. I do want to, so we also defined it down here, but I do want to mention that a chiral carbon, we can also use the word chiral center and stereo center, and those both mean the same thing, okay? All of those are referring to a chiral carbon, okay? So we'll use those words interchangeably, but they mean the same thing. Okay, so let's look at our example 1. Okay, let's keep our definition here. In the image below, there are how many groups attached to the carbon indicated by the arrow? So here is the carbon, right? And because it's a normal tetrahedral carbon, it will have 4 bonds to something, okay? So in the image below, there are 4 groups attached to this carbon, okay? And what are these 4 groups? Well, let's circle them. So we've got a methyl group, we've got an ethyl group, and then we can't forget that we have 2 invisible hydrogens here, okay? So listing these groups, we've got a methyl group, an ethyl group, we have a hydrogen and another hydrogen, okay? So, of these 4 groups, how many of them are unique? Well, the methyl, the ethyl, and then we get to the hydrogens. Now, the hydrogens are the same group, okay? They are identical. So this carbon right here only has 3 unique types of groups bonded to it. So is this carbon a stereocenter? The answer would be no. It is not, because remember, what's the definition of a stereocenter? Well, remember, stereocenter is the same thing as a chiral carbon. So what do we need in order to be a chiral carbon? Well, we need a carbon that's bonded to 4 different groups. So no, this is not a stereocenter because the carbon is not bonded to 4 unique groups. Okay? All right, example 2. In the image below, there are how many groups attached to the carbon indicated by the arrow? Well, here we go. So again, it's a normal tetrahedral carbon, and so it has an invisible hydrogen here, which means that this carbon does have 4 groups attached to it, okay? And what are these 4 groups? Well, let's highlight them. We've got a methyl, a hydrogen, an OH group, and an ethyl group. Okay, so the 4 groups are a methyl group, an ethyl group, an OH, and a hydrogen. So of the 4 different groups that we have here, how many of them are unique? Well, all 4 of them are unique from each other. So is this carbon a stereocenter? Well, the answer will be yes. Why? Because it is bonded to 4 unique groups. Okay? So, now let's dive into, now that we can identify a chiral carbon, let's look at some interesting things about chiral carbons. Because this carbon, well, we're going to be drawing the same picture down here, okay? So that is the same molecule here. So because this carbon is chiral, there are two possible arrangements for this particular carbon, okay? So what we have drawn here, let's ignore this real quick. We have this molecule versus this molecule. Notice they're both seem very similar, and they are in fact mirror images of each other, okay? So pretend that these dashed lines is an invisible mirror, okay? Now, if I want to compare these molecules, okay, they are actually not identical. So what I've drawn here is I have a little book. So pretend that this is a book that's open, okay? Now what I want to do is I want to take this molecule and I want to flip it as if it was a piece of paper and flip it over, okay? So I'm not going to change the molecule. All I'm going to do is rotate it as if it was a page and I was going backwards one page, okay? So if I just take this page and I plop it right there, how would the molecule look in space? Well, it would look like this, okay? So if I take this molecule with the OH coming out in front of the page and I sort of flop it over to the next page, the OH, which at first was coming out of the page, will now be going back behind the page, and you can see it's on the dash. The hydrogen, which originally is going back when we flip the page over, is now going to be coming out in front of the plane of the page, okay? So this molecule and this molecule are identical, okay? The way I got to this molecule was I just rotated this one. So the question is, how does this molecule relate to this molecule? Well, what I'm going to do is I'm going to cut this out and we're going to bring it over here. So notice how the carbon chains line up like that. All right. So you can see everything lines up. Let me erase that. All right, so everything lines up. The OH and the OH are next to each other, and the hydrogen and hydrogen are next to each other. The only problem here is they are not perfectly overlapping, because notice in the red structure, the OH is going in the back, it's on a dash, whereas in the black structure, the OH is actually on the wedge coming forward. So these molecules, okay, this one and this one are not identical. And the way that I know that they're not identical is because no matter how I manipulate this one, no matter how I rotate it, okay, even when I rotated it like this, I cannot superimpose this molecule onto the black molecule, okay? So to superimpose means that I can put two objects on each other and they will exist perfectly in the same way, in the same space. So my hands are a good example. These are mirror images. So you can see they are mirror images, but if I try to take them and superimpose them on each other, my thumbs will be overhanging. So these two hands, when they're mirror images, well, they are mirror images, but they are not superimposable because they do not occupy the same space, okay? And so that's what happens with chiral carbons. You can have a chiral carbon, and if you draw its mirror image, they will not be superimposable to each other. And because they're not superimposable, because they can't occupy the same space, they are not identical, and therefore we need to have a way of distinguishing these two compounds. All right, so in the next video, we will be going over determining RNS, and RNS is just a way of distinguishing these two chiral carbons from each other, okay?